The clock hits 0 and the room is silent. On the big screen, an icon says, "Entry interface." No cheers, no countdown. Because on Mars, by the time a signal reaches Earth, the landing has already happened. Those 7 minutes between first touch of atmosphere and first breath on the surface decide everything: mission, success, or a hole you will never see. Imagine being the spacecraft. You have crossed tens of millions of miles to meet an ocean of air that is almost not there. It is under 1% of Earth's pressure, thin like stratosphere air, yet you are hitting it at Mach 20. Your heat shield lights up like a star. You cannot steer with hands or wings. You have one chance to turn hypersonic chaos into a soft, upright landing, and there is no live help from home. This is the deadliest 7 minutes in exploration. Engineers call it EDL, entry, descent, and landing. It sounds simple, 3 words for falling, but it is one of the most brutal gauntlets any machine is asked to run. Too steep and you burn or skip. Too shallow and you bounce back into space. Too heavy and the parachute rips. Too light and the winds throw you like a leaf. Even the dust fights you, carrying static, hiding rocks, swallowing radar. We romanticize Mars as the next home, but Mars is not welcoming. The atmosphere is thick enough to set you on fire and thin enough to fail you when you try to slow down. On Earth, a parachute can tame a capsule from supersonic speeds. On Mars, a parachute the size of a house is still fighting air that barely cares. You hope the fabric and lines survive the shock. People remember the phrase, 7 minutes of terror from curiosity and perseverance. It is not a slogan. It is a summary of the physics. The spacecraft must do a dozen things at exactly the right times without a single command from Earth. Orient the heat shield, bank to bleed speed, jettison the shield, deploy a supersonic parachute, sense the ground through plasma and dust, cut the chute before it kills you, fire rockets, lower the rover on a cable, and fly the jetpack away to crash at a safe distance. It has gone wrong. It will go wrong again. A guidance computer once believed it was underground while it was still 2 miles up. Engines cut. The vehicle met Mars the hard way. A famous orbiter was lost because one team used pounds and another used newtons. Navigation followed the wrong numbers into the atmosphere. A small British lander touched down, then never phoned home because its solar panels were trapped under petals that did not fully open. On Mars, tiny mistakes are amplified by speed, heat, and distance. So, why keep trying? Because every success changes what is possible next. Viking taught us how to land heavy probes with rockets. Pathfinder showed we could bounce on airbags and still roll away. Phoenix proved we could touch down near polar ice. Curiosity and perseverance invented flying cranes, the sky crane maneuver, lowering a 1-ton rover while the jetpack hovers. Each breakthrough becomes a tool against the planet's indifference. Here is the heart of the problem. Mars sits in the cruel middle. It is not dense enough for wings to carry you like on Earth, and not airless enough to let you fall and break only with rockets like on the Moon. You must blend heat shield aerodynamics, supersonic parachutes, and powered descent in one continuous choreography. Get the timing or the sequence wrong, and the whole dance collapses. And the planet fights back with weather. Dust storms rise to global scales, changing air density and temperature. Winds shear from layer to layer, pushing you sideways during the most delicate moments. Terrain is a minefield of boulders and slopes. The rover wants science, which lives in dangerous places, river deltas, crater rims, ancient lake beds, exactly where landing is hardest. That is why the newest craft carry eyes and brains to pick a safe spot in real time, comparing camera views to onboard maps and making the call as they fall. But do not confuse precision with safety. A perfect target does not help if the parachute tears or if the guidance computer believes a lie. That is why the choreography has grown smarter and more redundant. Supersonic parachutes are now stress-tested in wind tunnels and by rockets. Terrain relative navigation gives the vehicle a sense of place. The sky crane keeps the rover's wheels clear of dust and debris from rocket plumes. Each step answers a failure we have already lived through. We call these minutes terror because humans do not get to intervene. We are not terrified of Mars. We are terrified of silence. From the moment entry begins, radio transmissions bend and fade, wrapped in plasma and delayed by millions of kilometers. By the time a tone reaches the dish in California, the spacecraft has either solved its own murder mystery or become a new crater with no witnesses. The control room does not control anything. It only listens for a heartbeat. Here is the promise and the cliffhanger. Over the next 2 hours, we will unpack the hardest landing sequence in the solar system. Look inside the thin air that both saves and betrays you. Decode the physics of hypersonic flight, supersonic parachutes, and the jetpack that lowers a car with a rope. Dissect the failures and the fixes from metric mix-ups to sensor illusions and explore new strategies. Bigger heat shields, inflatable decelerators, and deep throttling rockets that might finally make Mars landings feel routine. If you have ever wondered why Mars turns brilliant engineering into a gamble, stay with me. The next 7 minutes decide the next 7 decades, and it all starts with a single line on a screen. Entry, interface. Mars doesn't let you muscle your way in. To survive entry, descent, and landing, you have to turn thin air, hot plasma, and milliseconds of timing into tools. The Martian atmosphere is mostly carbon dioxide and only about 1% as dense as Earth's. At sea level, too thin to slow a heavy vehicle with parachutes alone, too thick to ignore when you're screaming in at hypersonic speed. So you show up wrapped in a blunt aeroshell, a flying saucer that trades elegance for drag. The blunt shape builds a strong shockwave in front of you, pushing superheated gas away and turning murderous speed into manageable heat on your ablative heat shield. Engineers obsess over a number called the ballistic coefficient mass divided by reference area. Lower is better on Mars. More area, less mass, more drag, more time to live. But the aeroshell is more than a shield. It's a steerable body. Since Viking, Mars landers have flown their heat shields. By rolling to a commanded bank angle, the capsule generates a small lift vector, just enough to surf a corridor in the atmosphere. That guided entry shrinks the landing ellipse and manages both heating and G-loads. Dive too steep and heat flux spikes, ablative material boils away, and structures are punished. Come in too shallow, and you bleed speed so slowly that you run out of sky. In the middle lies a thin band of just right, and the only way to stay in it is to fly. Inside the shell, the onboard computer is solving a murder mystery in which it is the victim. Accelerometers and gyros track motion, while the outside world is hidden behind a cone of plasma. Pressure ports sniff the air to infer dynamic pressure and Mach number. Those measurements feed a state estimator that decides when it's safe to take the next irreversible step. Triggers are set on velocity and deceleration, not just altitude, because altitude lies during dust storms. Density changes with temperature and weather. Relying on height alone can fire events too early or too late. The vehicle must read the air it actually has, not the air a model promised. Then comes the maneuver that sounds wrong until you remember the thinness of Mars. You deploy a parachute while still supersonic. On Earth, you wait until subsonic flow to avoid shredding the canopy. On Mars, if you wait that long, you'll meet the ground first. The answer is a disc gap band parachute, a ringed, vented design that stays stable in shock-riddled flow. Its opening shock is brutal loads slam into the risers in a blink, so these canopies get tortured on Earth before they ever see Mars. In wind tunnels and rocket-powered tests that yank them open at Mach numbers you feel in your ribs. Once the chute is working, the heat shield can go. That one separation turns a blind, burning stone into a spacecraft with eyes. Radar altimeters begin to ping the ground. LiDAR samples slopes. Down-looking cameras start terrain, relative navigation. A trick that lets the vehicle recognize Mars like a pilot recognizes a hometown from above. The computer carries a map built from orbital images. It compares live pictures to that map in real time, locking onto craters, mesas, and shadow patterns. If the projected landing point sits on a boulder field or a steep apron, the guidance shifts the aim point sideways, using the parachute and residual lift to slide towards safer ground. Eventually, the parachute becomes the enemy. You're still moving fast, the terrain is close, and staying leashed to a giant sail will kill you if rockets light. So there's a clean cut. The back shell and parachute drop away, and the descent stage fires its engines. Here, Mars's thinness helps again. Plumes are broader and less likely to dig deep holes than on the Moon, but they still kick up curtains of dust that can blind cameras and sandblast hardware. Throttle response matters. If engines overreact to a gust, they can crater the site or slam the vehicle with debris at the worst possible moment. This is where the sky crane earns its legend. Lowering a rover on tethers from a hovering jetpack looks theatrical, but it solves three traps at once. First, it keeps rocket plumes high, so the rover isn't bathed in grit at the moment its sensors and optics matter most. Second, it avoids ramps from a tall lander deck. The wheels touch the terrain they'll drive on. Day one, no risky bridge. Third, it keeps the center of gravity low, so the rover doesn't topple in the first second of Mars life. When weight on wheels is sensed, pyros cut the bridles, the jetpack throttles up and flies itself away to die quietly a safe distance off. The star of the show is left alone, clean, and ready to roll. Could we just bounce again, like Pathfinder and the Mars exploration rovers? Airbags were brilliant for a few hundred kilograms. Light, tolerant of rough ground, mechanically simple. But airbags don't scale gracefully. As mass rises, the bags grow heavy. Inflation loads soar, and sharp rocks become lethal. For small stationary platforms like Phoenix, legs and throttleable engines are efficient. For car-sized rovers, cranes hit the sweet spot. And for cargo and cruise, we will need even more. One frontier is bigger, softer entry systems. Inflatable or deployable aeroshells, think gigantic donuts packed tight for launch, then bloom into wide drag devices before entry. Bigger diameter means a lower ballistic coefficient and earlier, gentler deceleration higher up, where heating is kinder. Another frontier is supersonic retropropulsion. Firing powerful engines forward while still supersonic, so thrust replaces the drag the thin air can't provide. The physics works. The challenge is guidance, engine stability in wild flow, and making sure you don't fly through your own exhaust. Both lines of attack are about buying time, seconds more to sense, decide, and correct. Software and timing are evolving too. Range-triggered parachute deployment uses sensed deceleration and the vehicle's estimated position to pick the moment, rather than a single predicted altitude that weather can betray. Predictive guidance models, gusts, and density variations on the fly. Hazard detectors build a 3D map of rocks and slopes and veto landing zones that would flip or trap a rover. The choreography is still automatic. Mars won't wait for humans to think, but it is no longer blind. The vehicle carries enough knowledge of the neighborhood to choose where not to die. Even the old parts are being rewritten. Parachutes gain stronger weaves and novel reinforcement patterns that spread opening shock. Heat shields trade classic ablators for advanced materials that char predictably and can be tiled to handle local hotspots. Descent engines learn to throttle deeper and faster without excavating the site. Radars shape their beams to see through blowing dust. Cameras widen their dynamic range so sunlit haze and shadowed rocks can be read in the same frame. Every upgrade is a scar remembered from a past mission, a failure turned into a feature. If this still sounds like theater, remember it's driven by arithmetic. The air is thin, gravity is real, and the ground is hard. You stack tools in a strict order area: lift, parachute, sensors, rockets, cables, so each buys the seconds the next one needs. Miss a handoff and the chain snaps. When it works, touchdown looks casual, almost inevitable, as if Mars finally agreed to let us stay. But the grace is paid for by years of wind tunnel runs, rocket sleds, vacuum chambers, hardware ripped apart on purpose, and software rehearsals that try to break the pilot before the planet can. That is the bargain of EDL. Design the fall so precisely that it feels like flying. To understand why the 7 minutes are so unforgiving, see Mars as a tricky fluid machine. Start with density. Near the ground, pressure sits at a few millibars, about 1% of Earth, so drag is scarce. Composition? Mostly carbon dioxide, lowering the speed of sound. At the same true speed, you run a higher Mach number. Shocks appear sooner. Temperature swings wildly, so the same altitude can feel like a different planet hour to hour. That variability is the first enemy of timing. Entry is hypersonic, several kilometers per second. The flow piles up into a detached shock just ahead of the aeroshell. Behind it, molecules compress, heat, and partly ionize. The craft hides behind an ablative shield that chars and peels to carry heat away. Think of it as a sacrificial brake pad. Materials progressed from Viking's ablators to modern Pika-class shields that keep mass low while soaking up brutal heat pulses. The shield alone doesn't deliver you to safety. A ballistic fall lands where winds choose. Mars landers, therefore, fly their shields by banking to create a little lift. Lift buys steering, dip deeper for more drag, ride higher to limit heating, slide cross-range toward a chosen corridor. Engineers obsess over ballistic coefficient mass divided by reference area because on Mars, lower is life. Big area and disciplined mass budgets buy seconds to think. Then the room goes quiet. Shock-heated gas becomes a thin plasma that blocks radio, so Earth hears nothing during peak heating and deceleration. There is no joystick rescue. Guidance must infer state from inertial sensors and pressure ports and proceed. When the Deep Space Network hears again, many irreversible steps have already fired. What goes wrong most? Timing. Key events: heat shield drop, parachute deployment, backshell separation, engine ignition are triggered by sensed deceleration and velocity, not altitude alone, because Martian altitude lies. Warm dust can thin the air at a given height, making you deploy higher and faster than intended. Cold, dense air can stall triggers until the ground is too near. Even a perfect script slips if winds rotate you off the expected attitude. Sensors can also mislead. An inertial unit can clip during peak G, starving the estimator for a heartbeat. A radar altimeter can latch onto a slanted wall and report phantom ground. LIDAR can saturate in its own dust. Cameras used for terrain, relative navigation can lose contrast in hazy noon or be blown out by glare. Modern vehicles fight back with redundancy and voting, multiple sensors, different modalities, and algorithms that distrust any source that disagrees with the crowd. Parachutes earn their reputation as heartbreakers. On Mars, you must open them while still supersonic, accepting a brutal opening shock. Disc gap band and ring sail designs stay stable in shock-riddled flow, but loads travel through fabric and lines in milliseconds. If anything tears in that first half second, there is no second chance. Teams therefore torture canopies on Earth, mortar shots, rocket pulls, reinforcing weak seams until the pattern survives the violence. Rockets fix what parachutes can't and introduce new traps. Light them too early and plume. Shock interactions can destabilize the stack. Light them too late and you're simply decorating the surface. Even when timed perfectly, plumes reflect off the ground. dig pits, and fling stones. The sky crane keeps engines high and the rover low, avoiding dust baths, ditching ramps, and lowering the center of gravity right at touchdown. For legged landers, deep throttling engines and careful nozzle angles try to tame plume impingement and side forces. Scaling punishes shortcuts. Airbags were genius for a few 100-kilogram payload, but fabric mass, inflation pressure, and rock vulnerability grow faster than payload. What's elegant for a small lander becomes punishing for a 1-ton rover. Likewise, with guidance, a law tuned for one heat shield and center of gravity can misbehave when geometry changes. EDL is never copy and paste. Each mission repeats the outline but rewrites the details. Terrain raises the stakes. The safest planes are often scientifically dull. The richest targets, ancient deltas, crater rims, layered lake beds, are littered with boulders and slopes. That's why the new playbook adds terrain relative navigation and hazard detection. The vehicle carries an orbital map, then compares live camera views to that map in real time. If the projected touchdown is nasty, guidance slides sideways into a safer pocket before cutting the chute or lighting rockets. Meanwhile, the atmosphere keeps changing. Daily temperature cycles puff the air by afternoon and let it sag at night. Seasonal dust warms middle layers and thins the lower ones. Vertical wind shear can shove you sideways the moment the parachute is fighting to stay centered. Designers therefore moved from single-number triggers to range-triggered logic that watches what the vehicle actually feels, deceleration history, estimated range to target, wind cues, and decides on the fly. So why do Mars landings keep failing? Because there are a dozen ways for a narrow timing chain to slip, and slipping at Mach numbers can be fatal. Why do they keep succeeding? Because each scar becomes a safeguard. Better ablators hold the shock at bay longer. Bigger, sometimes inflatable aeroshells lower ballistic coefficient, so you start slowing higher, where heating is kinder and decisions are less rushed. Stronger supersonic parachutes buy altitude, then get cut before they can drag you sideways. Deep throttling engines expand the controllable envelope during the final tens of meters. In short, the deadliest 7 minutes aren't a monster to slay once. They're a dance to rehearse until the steps are second nature. Thin air hurts and helps. Dust hides the ground and warms the sky. Parachutes save you and threaten you. Rockets control your fate and try to bury you. Mastery comes from stacking these contradictions, so each buys seconds for the next. When the choreography works, touchdown looks casual, as if Mars relented. It didn't. You just learned its rules. Next, we'll lay out the minute-by-minute timeline of a modern EDL, the cues and split-second handoffs before we autopsy the infamous losses and what they taught about units, sensors, and humility. Minute zero arrives without a countdown. In deep space, the cruise stage has already peeled away. The rover and its aeroshell roll to a knife-edge attitude and fire tiny thrusters to thread an invisible doorway, an entry corridor a few degrees wide. Too high, you skip. Too low, you cook. The onboard clock hits the mark, and the vehicle feels the first whisper of carbon dioxide 120 kilometers up. Entry interface. Seconds later, the ship grows a star. Ram air slams the blunt shield and detonates into a shock front. Molecules compress, ionize, and glow. A sheath of plasma cocoons the vehicle and radio cannot pass. Inside, accelerometers spike as deceleration climbs 4, 6, then 10 G for a few brutal breaths. The heat shield ablates on purpose, charring and sloughing, converting heat into chemistry and ash. This is the guided fall. The capsule banks, rolls, and reverses, S-turns, at Mach numbers that look unreal. A small lift vector builds under the aeroshell, just enough to surf density layers and steer cross-range. Guidance watches deceleration history like a cardiogram. If drag runs high, it rides a bit higher to spare the shield. If the air is thin, it digs deeper to buy time. The aim is simple and hard. Reach a specific speed, altitude, and range when the parachute wakes. 2 to 3 minutes after entry, heating eases. Peak deceleration passes. The plasma thins. Now the vehicle has to gamble on a fabric the size of a house. On Mars, you cannot wait for subsonic. You must throw your parachute into supersonic flow. A mortar punches the packed canopy into the airstream. It blooms in a violent fraction of a second. Lines snapping taut with a crack you can feel in telemetry. Loads ripple through seams and risers. If the weave holds, you live to take the next step. Parachute deployment is range-triggered. The vehicle doesn't use a single predicted altitude. It combines sensed speed, deceleration, and estimated distance to target to pick the moment. This avoids deploying too high on a warm, thin day or too low on a cold, dense one. If the math says wait, it waits. If it says go, it commits. There is no second shoot. With the canopy biting, the next irreversible cut arrives. Jettison the heat shield. Explosive bolts pop. The charred dish falls away, and the rover's eyes open to Mars. A radar altimeter wakes and throws chirps at the ground. A scanning LiDAR samples slopes. A downward camera snaps rapid images that feed terrain relative navigation. The computer carries an onboard atlas made from orbital imagery. It compares live views to that atlas in real time, locking onto craters and ridges to estimate position and heading. Dust tries to ruin the trick. The vision system compensates with high dynamic range and algorithms that favor bold features over fragile texture. Meanwhile, winds tug the canopy. The stack swings. The vehicle damps the motion so the line to the rover stays reasonably straight. Seconds are melting. Altitude collapses. Velocity remains stubborn. The parachute has done all it can. Now, it becomes a liability. Below, the landing site fills the frame. The flight computer marks a safe pocket, then makes another decision: cut away. The backshell and chute separate, and the descent stage lights its engines. Mars, thin as it is, takes the blast and throws up a tan curtain. The powered phase is a balancing act with gravity and dust. Multiple thrusters throttle quickly, hunting a sweet spot where descent is steady, but the plumes don't dig a crater and spray stones. Guidance blends radar, LiDAR, and inertial estimates, filtering out lies kicked up by the dust cloud. The vehicle flies aslant toward the chosen pocket, then rotates to a near vertical drop. The clock is counting in heartbeats. At roughly a couple thousand meters per minute, walking speed to sprint speed relative to the ground, depending on design, the engines pull the stack into a hover-like glide. Old landers extended legs and rode the rocket all the way down. Rovers have a different choreography. The descent stage earns its legend, and the sky crane begins. Tethers pay out. A belly umbilical lowers the rover, wheels already spread and locked. The cable trick keeps engines far from the ground, avoids risky ramps, and plants the center of mass low and stable at first contact. The winch meters the drop with centimeter precision. The rover watches the world approach in LiDAR frames. Rock edges, shadow lines, a shallow ramp of dust leading into the safe pocket chosen from above. Touchdown is not a shout. It is a sentence of small verbs. Wheels kiss regolith. Load cells feel weight. Accelerometers shift from falling to standing. Software recognizes the signatures and fires pyros that cut the bridles. The umbilical severs. Above, the descent stage snaps free and throttles hard, pitching to a flyaway. It aims for a planned crash zone hundreds of meters off, far from science targets, leaving only a distant thud and a fading plume. Silence follows, then the first breath, a healthy tone, a thumbnail image, a spectrum that proves the radio survived the dust. In the control room, cheers chase, a tight-lipped minute of verification. Health packets green, pressures nominal, temperatures sane. The rover unfolds a little, yawns its mast, sniffs the wind. Somewhere on a red plain, a new student in an old school of exploration learns how Mars tastes. All of that fits into roughly 7 minutes between the first touch of air and the first touch of stone. Exact times vary planet geometry, vehicle mass, and whether stretch or squeeze the choreography, but the handoffs are consistent. Heat shield, guidance, parachute, vision, cutaway, rockets, tethers, touch, fly away. Each step is a bet that the next will work, paid for by ground tests that tried to break it first. That is the minute-by-minute story. Next, we autopsy the famous losses, what happened to the Mars Climate Orbiter, the Polar Lander, Schiaparelli, and Beagle 2, and the rules their failures wrote. Autopsies matter, because failures write the rules everyone else follows. 4 names still haunt Mars mission planners: Mars Climate Orbiter, Mars Polar Lander, Beagle 2, and Schiaparelli. Each met Mars differently. Together, they map the minefield between atmosphere and ground. Start with the quietest catastrophe, Mars Climate Orbiter in 1999. It was not an EDL drama, but a navigation tragedy at the doorway to aerobraking. The spacecraft was supposed to skim the upper atmosphere in repeated passes to circularize its orbit. A groundside tool produced impulse data in pound-force seconds, while the flight dynamics software expected Newton seconds. The mismatch was tiny per maneuver and fatal in aggregate. Over weeks, the trajectory drifted downward. At the crucial periapsis, the orbiter dipped into air dense enough to overwhelm the plan. Heating, dynamic pressure, and guidance uncertainties compounded. Communication ended. A unit error on Earth had written a fate on Mars. The same year brought a second lesson: Mars Polar Lander. The lander rode a parachute and rockets toward a southern latitude site, while 2 tiny impact probes, Deep Space 2, detached to make their own dives. MPL carried a 3-legged platform with touchdown switches. During descent, the legs deployed and locked, producing a brief electrical signature. The landing software interpreted that blip as contact with the ground. Engines shut down early, likely tens of meters above the surface, and the vehicle fell the rest of the way. No call home, no pictures, just silence. Investigators also criticized the relay plan, which left coverage gaps and flagged uncertainties in parachute and backshell sequencing. But the central lesson was brutal. Do not let a transient sensor echo masquerade as landed. Beagle 2, 2003, delivered a different heartbreak, probably a successful landing followed by silence. Years later, high-resolution orbital images revealed the lander on the ground with bright patches consistent with partially opened solar panels. The most plausible explanation is a single panel that failed to swing clear, pinning another and blocking the UHF antenna's view of space. Power may have been available. The transmitter simply had no clear path. The morals are old but sharp. Deployment chains must be testable end to end under flight-like loads. Critical radios and sensors should not be vulnerable to one stuck hinge. Fast forward to 2016 and ESA's ExoMars Schiaparelli entry, Descent and Landing Demonstrator Module. After the supersonic parachute deployed, the vehicle performed a rotation that briefly saturated its inertial measurement unit. That second of clipped data poisoned the state estimate. Guidance concluded the craft was below ground level and declared landed. It jettisoned the backshell, cut the parachute, and fired the descent engines for only a few seconds instead of the planned burn. Schiaparelli separated from its parachute high above the surface and fell, leaving a fresh scar on a plane. One saturated sensor, one brittle logic path, one crater. 4 episodes, one theme. Mars punishes brittle assumptions. The fixes start with ruthless interface discipline. Units and frames must be treated as executable requirements, not footnotes. Build automated checks into simulation and operations pipelines so a pound cannot sneak into a Newton world. require independent navigation reconstructions by separate teams using different software. Next, tame sensor illusions. Leg switches chatter, radars lock onto sloping walls and report phantom ground. IMUs clip under peak loads. Cameras lose contrast in dust and glare. The remedy is diversity with voting and sanity checks. If radar claims the ground jumped upward but the vertical velocity and thrust say otherwise, stall the trigger and remeasure. If an IMU clips, flag the estimate, inflate uncertainties, and block any mode change that assumes precise altitude. Make landed a consensus, not a hunch. Third, design for ugly deployments. Mechanisms that behave in clean rooms may sulk in cold, vibration, and dust. Test them until they complain shock, vibration, vacuum thermal cycles, and dust intrusion, and design to fail safe. Place antennas so one stuck hinge cannot smother them. Provide a minimal "I am alive" beacon on an independent path. Ensure a late-cut tether cannot tip the vehicle. Fourth, treat timing as estimation, not a stopwatch. Mars is not a metronome. Warm dust thins the air. Cold nights thicken it. Range-triggered events use sense deceleration history and estimated position to choose moments, reducing dependence on a single altitude callout. Add guardrails, require multiple lines of evidence for irreversible steps, and carry propellant and battery margins sized for weather, not for averages. Fifth, respect scale. A technique proven at one mass may misbehave at another. Airbags that coddled a 180-kilogram rover become heavy, fragile liabilities near a ton. Parachutes stable for one geometry flutter for another. The countermeasure is humility. Treat every mission as a new EDL. Requalify chutes at relevant Mach numbers. Retune guidance to the exact aerodynamics and center of gravity. You will fly and shake, bake, and yank the hardware until it tells you where it breaks. There are softer lessons, too. Communications gaps during the critical minutes compound risk. MPL depended on a relay geometry that left long stretches of silence. When things went wrong, the ground heard nothing that could guide recovery. Today's playbook favors multiple links direct to Earth tones, UHF relays through orbiters, and robust breadcrumb beacons that keep whispering even through plasma blackouts. Telemetry you never see cannot save you, and culture matters. The most valuable artifact is not a parachute or a heat shield. It is an organization that assumes it is wrong and works to prove itself right. Modern Mars teams schedule independent reviews by separate groups, run cross-checks with different software stacks, and hold premortems that ask how the mission could die before hardware ships. Notice how each scar became a safeguard. Parachute deployments moved to range-triggered logic. Terrain relative navigation gave vehicles a sense of place to defeat dust and haze. Descent engines learned deeper throttles with faster response. Radars gained smarter filters to ignore echoes that do not fit the physics of the fall. Beagle 2's silence pushed designers to relocate radios and add backup beacons. Schiaparelli's clip taught guidance to distrust impossible altitudes. Failures are tuition. Mars will keep charging, but the bill can be paid in advance. That is how you turn the deadliest 7 minutes into a procedure you can do again. How do you prove a choreography this unforgiving before you ever touch Mars? You abuse it on Earth. EDL is forged in 3 labs: numbers, wind, and fire. The numbers lab builds the first draft CFD for shocks and heating, and 6 degree of freedom simulations that fly a virtual vehicle through millions of what-ifs. Monte Carlo runs randomized winds, density, center of gravity shifts, and sensor noise. Weak algorithms die here, not at Mars. Wind is the second lab. Hypersonic tunnels map pressure and heat, so the ablator can be tailored like armor. Subsonic and transonic tunnels torture canopies, hunting instabilities that turn a parachute into a flapping drum. Rocket-borne drop tests hurl full-scale chutes into thin, fast air, so they feel the same violent yank they will face on Mars. Fire is the last teacher. Arc jet facilities blast heat shields with plasma streams until models match reality. On stands, descent engines throttle through final kilometer duty cycles while instruments watch for oscillations, valve lag, and flow separation. Technicians add dust to measure what a landing site will suffer. Parachutes earned a renaissance because Mars demands supersonic openings. Disc gap band and ring sail canopies were redesigned to bloom in an eye blink and hold attitude in shock-riddled flow. The art is choosing the dynamic pressure to fire the mortar. Too high and the canopy shreds, too low and it inflates weakly and tumbles. Sounding rocket campaigns pulled full-scale chutes at Mars like Mach numbers and mapped loads with strain gauges. Beyond fabric, the frontier is bigger. Softer entry systems, deployable and inflatable decelerators that pack under a fairing and bloom to dish-like sizes in space. A larger diameter lowers ballistic coefficient, starting the slowdown higher where heating is kinder and guidance has time to think. Recent demonstrations proved that giant, flexible aeroshells can ride hypersonic and survive Earth re-entry, evidence that the concept scales. On the rocket side, a once taboo phrase became a strategy: supersonic retropropulsion. Returning boosters on Earth showed that thrust can carve a controllable bubble in oncoming flow and ride it. Dense air at home is not the wispy CO2s of Mars, but the data changed the conversation. Retropropulsion offers what parachutes cannot: deceleration that scales with mass and obeys a throttle. Now zoom into the sky crane, the maneuver that turns skepticism into photographs of delta rocks. A rocket-powered stage pays out 3 bridles and an umbilical, while a winch meters descent in centimeters per second. Lowering keeps engines high, dust away, and the rover's center of mass low. Touchdown triggers cuts and a fly, away to a safe crash. All that choreography is run by computers that would not impress your phone, but they are predictable and radiation tolerant. Flight software is a garden of guarded doors, state machines, watchdogs, and interlocks that refuse to open if the world looks wrong. Developers inject faults by the 1,000 frozen gyros, blinded cameras, clipped IMUs, lying radars, until every single lie is caught by redundancy and voting. Precision landing is the other half of survival. Terrain relative navigation gives a falling robot a pilot's intuition, matching live images to an onboard atlas to estimate position and heading. Hazard detectors build a 3D map of rocks and slopes and veto patches that would flip or trap a rover. Then guidance sidesteps into a safer pocket. Scale is the coming boss fight. A 1-ton rover demanded a sky crane. Tens of tons will demand huge aeroshells, perhaps no, parachute profiles, deep throttling engines, and landing pads to tame dust. Physics does not change, but margins do. Thin air stays thin, gravity stays gravity, and risk multiplies with mass unless you buy back seconds everywhere. None of this matters if the story ends in silence, so communications is treated like life support. During entry, a minimalist tone may wink through plasma, while orbiters relay richer telemetry. After touchdown, the vehicle triages: a heartbeat first, a thumbnail next, then the flood of health. If this sounds like paranoia with rockets, good. Paranoia is how you turn a planet's indifference into routine. Every torn chute becomes a stronger weave. Every clipped IMU becomes a logic patch. Every dust, blinded radar becomes a dual sensor map. In the end, 7 minutes of terror is the price you pay until practice makes the terror boring. Boring is the goal. The rover is alive, the cameras are warm, and the fresh crater on the horizon belongs to the discarded jetpack, not the mission. Next, we look outward. How the thin air itself behaves: seasonal dust, thermal tides, and upslope winds, and how forecasting that living atmosphere can make or break the exact moment a parachute wakes or an engine lights. Mars's air is thin, but it's alive. If you want to land, you don't just compute a trajectory, you forecast a mood. Start with the daily heartbeat, thermal tides. As sunlight heats dust and ground, the atmosphere swells, and the surface pressure oscillates with the sun's rhythm, peaking and dipping every Martian day. Those breaths swing density by noticeable percentages. For a falling spacecraft, a 5–10% change in density is not trivia. Dynamic pressure scales with density, and dynamic pressure governs heating, deceleration, and when your parachute will survive the brutal yank of deployment. A warm, puffed-up afternoon atmosphere lowers density at a given altitude and delays deceleration. A cold pre-dawn sky thickens the air and grabs harder, sooner. If your triggers were tied to a single height above ground, the tide would trick you. This is why modern EDL logic watches what the vehicle actually feels, deceleration history, Mach, and inferred range, and only then commits to irreversible actions. Dust is the amplifier. Mars grows dust storms like Earth grows weather fronts, and sometimes they encircle the planet. Dust grains suspended in CO2 soak up sunlight and heat the air aloft, lifting the scale height and redistributing density vertically. Down low, thinner air than the maps promised. Up higher, more buoyant layers than your models liked. That vertical reshuffling shifts the wear and win of peak heating, moves the safe window for parachute opening, and changes how hard winds tug the canopy. It also changes what cameras see. More haze, less contrast, more glare, a problem for terrain, relative navigation that wants crisp craters and sharp shadows. Vision systems fight back with high dynamic range and by latching onto bold, high-contrast features, but a world wrapped in tan can still steal precious matches from the algorithm. Then there's the choreography of winds. In the mid-latitudes, baroclinic waves spin storm tracks around the planet, carving jet-like currents and shears between layers. Near mountains and crater rims, slope flows rule. Upslope winds by day as sunlit air climbs terrain. Downslope by night as cold, dense air drains like water. Fly through those layers on a parachute, and the stack can yaw and swing. Guidance damps the pendulum, but if shear gets strong enough at the wrong moment, it can tilt the canopy, load risers asymmetrically, and spoil the clean line your descent stage wants when it lights engines. Even a few degrees of unexpected attitude at cutaway can force rockets to spend their first seconds fighting geometry instead of gravity. Season matters, too. Mars tilts like Earth and runs through springs and winters that reshape circulation. Polar hood clouds and CO2's frost change thermal gradients, moving jet cores and altering where dust likes to form. Entry plan for southern spring will not feel like one in northern fall. The same nominal profile yields different actual density histories, different winds, different risk. Mission designers bake this into arrival timing, picking a season and local time that balance density, winds, lighting for navigation cameras, and relay geometry to orbiters waiting overhead. Forecasting is its own mission. Orbiters map dust, opacity, and vertical temperature profiles day after day, building the inputs for Mars climate models. Ground packages on past landers and rovers record surface pressure, temperature, wind, dust devils, and boundary layer turbulence, feeding back truth data. Put it all together and you get an atmospheric nowcast and short-range forecast for the target site and season. Before entry, teams run ensembles, dozens to thousands of virtual Mars atmospheres consistent with recent observations. Each one runs an EDL through the timeline. If too many runs shred the parachute, overheat the shield, or force an engine light at a bad dynamic pressure, you adjust the guidance targets, the range trigger bands, or in extreme cases, the planned local time of entry. You can't wave off Mars like an airport, but you can slide the corridor by minutes and shave risk. The thin air also carries tricks at the ground. Dust devils, convective swirls that vacuum dust into tight columns, hint at strong daytime turbulence in the boundary layer. Touchdown amid that choppy air, and a legged lander can rock, or a hovering descent stage can fight to hold attitude. Rovers feel it too. Mast cameras shimmer in heat haze, anemometers click with grit, and power planning changes because dust load on the sky dims solar input or coats panels. EDL cares because turbulence modulates the radar, and LiDAR returns that estimate vertical speed and height. Filters must reject spurious spikes without lagging the truth. Haze isn't the only optical issue. Thin high clouds, water ice near morning or evening can brighten the sky and flatten shadows, reducing contrast when terrain, relative navigation, wants crisp edges. Designers answer with wider spectral response, exposure bracketing, and selecting local times when lighting geometry helps more than it hurts. A mid-afternoon landing buys warmer air and deeper boundary layers with more crosswinds but excellent illumination. A morning landing cools and calms the air a bit but shortens the day's first relay window to orbiters. Every choice trades one kind of stress for another. Even the quiet background pressure matters. The absolute surface pressure at the site sets the baseline density everywhere above it. Basins like Hellas sit deep and carry higher pressures. Highlands carry less. A low-pressure site steals drag you were counting on and pushes more of the deceleration job onto rockets. A higher pressure basin returns some drag but asks you to ride longer heating and manage a thicker, gustier boundary layer. Site selection weighs science value against these aerothermal realities. Ancient deltas in deep craters are treasure, but the air above them is not the same air above a plane. All of this flows into the EDL playbook as margins. Parachutes are qualified not to a single dynamic pressure, but to a band that covers seasons and dust states. Heat shields are sized for the worst credible heating integral, not the mean. Guidance carries buffers that let you slip S-turn energy management when density runs thin, and digs deeper when it runs thick. Engines are sized and throttled to handle late starts and gusts without digging craters. Terrain relative navigation doesn't just pick a pretty ellipse. It vetoes micro-hazards, boulder clusters, and slopes that are particularly unforgiving if dust veils the final meters. And still, Mars improvises. A regional storm can explode faster than yesterday's imagery suggested. A frontal wave can shove a last-minute shear into your parachute phase. A thermal tide's amplitude can spike during dust events, shifting density by double digits just when you need stability. The answer is not bravado, it's layered sensing and agile logic. If the radar claims the ground leapt upward while the inertial solution says you're still dropping fast, the software stalls landed and waits for agreement. If the LiDAR saturates in dust, the estimator inflates uncertainty and leans harder on radar and inertial cues. If deceleration runs low across the entry, range-triggered logic deploys the chute later and commands a deeper dig to recover the plan. Mars's air will never be tamed, it will only be anticipated. The art is to turn a breathing, dusty, sheared atmosphere into a timeline that still works, with sensors that can see through the lie of haze and algorithms that believe only what multiple sources confirm. Do that, and thin air becomes an ally, just enough drag to buy the seconds rockets need. Just enough visibility for a robot to recognize a safe patch of ground and claim it. The only way to land on Mars is to see, think, and act faster than your problems. Guidance, navigation, and control the brain, eyes, and hands of EDL. Turn a screaming fall into a sequence of precise moves. Start with the brain. Spacecraft flight computers are not the latest smartphones. They're conservative, radiation-tolerant machines chosen because they behave the same on a bad day as on a good one. Predictability beats raw speed. The software they run is built like a vault. State machines with guarded doors, watchdogs that bite if anything stutters, interlocks that demand multiple sources agree before an irreversible step proceeds. Navigation is the art of knowing where you are when the universe is trying to lie. During blackout behind the plasma sheath, inertial sensors, gyros, and accelerometers carry the load. They drift if left alone. So the trick is to reset them the moment the vehicle can see again. Pressure ports sniff dynamic pressure combined with shape and angle that reveals Mach and density. As soon as the heat shield drops, radar and LiDAR begin their chorus, measuring altitude and velocity straight down and sometimes obliquely to catch slope. A downward-looking camera adds memory to the mix. Terrain. Relative navigation compares live images to an onboard atlas built from orbital photos, recognizing craters and ridges like landmarks. Each sensor has a personality and a failure mode. The estimator, the brain's accountant, knows those quirks and weighs input accordingly, trusting none alone. Control is the hands. Tiny thrusters roll and bank the aeroshell to surf the thin air and manage heating and G-loads. When the parachute blooms, control shifts to damping swings so the stack doesn't pendulum itself into trouble. Cutaway is a choreography of millisecond pyros and clean separations. Engines ignite into a regime where every throttle pulse echoes from the ground. Control loops must be fast enough to catch gusts without exciting oscillations that dig craters. During sky crane, the winch meets out tether at a rate matched to descent, so the rover never swings under a moving crane like a wrecking ball. The most human part of the machine is its skepticism. Modern EDL logic treats landed like a rumor that must be confirmed. A leg switch goes high? Good. But not enough. Radar says altitude is 0? Interesting. But prove it. Accelerometers switch from falling to still? Now, we're getting somewhere. Only when multiple, independent truths align does the software cut bridles, shut engines, and declare success. That discipline was learned the hard way from a lander that believed a leg deployment blip was touchdown, from a demo that thought a saturated sensor meant it had burrowed underground. Seeing through dust and glare pushed vision systems to grow up. Cameras carry wider dynamic range, so bright haze and shadowed rocks can coexist without washing out. Image processing favors bold, high-contrast features, crater rims, mesa edges over fine texture that dust steals. Exposure bracketing can capture multiple looks in a blink, then the estimator fuses them. LiDAR adds a depth map when contrast is poor. Radar plays the stoic, less pretty, more reliable in tan storms. The point isn't a perfect picture, it's enough geometry to avoid a boulder field and plant wheels on a gentle slope. Why all this obsession with precision landing? Because science lives in places that hate landers. Delta fans sliced by ancient rivers, layered crater walls, benches along the rims of canyons. Early missions accepted 100-kilometer ellipses and hoped. Now ellipses shrink to handfuls of kilometers, then to pockets inside them that a robot can actually survive. Terrain relative navigation and hazard detection don't just pick a dot. They veto micro-hazards, rock clusters, ripples, and slopes on the final approach. Let's talk about the parachute one layer deeper, because on Mars it is both savior and saboteur. The disc gap band or ring sail designs are riddled with vents and rings to stay stable in shock-riddled flow. Engineers qualify them not at a single opening load, but across a band of dynamic pressures, because Mars's mood swings density by double digits. Mortar timing is commanded by range trigger logic. Deploy when deceleration history and estimated position say you've reached the right slice of sky, not when a clock says it's time. After it opens, riser loads can go asymmetric in shear. The guidance system trims and damps to keep the line straight for the cutaway and engine light. Then the parachute must become a memory. Hanging on even a second too long can drag the stack sideways or wrap the lines as engines try to take over. Heat shields have their own quiet heroism. Ablators now are engineered like recipes, with binder chemistries that char predictably and microstructures that carry heat away as material peels. Tiles or locally thick patches address hot spots where flow recirculates around protuberances. The shield separation system gets abused on Earth vacuum, thermal extremes, shock because a stubborn bolt at Mars is a mission ender. When it drops cleanly, sensors wake and the blind fall becomes a guided descent. Descent engines close the gap where air can't help. Deep throttling is the superpower. You want thrust to range from strong enough to arrest a fall to low enough to avoid a dust geyser. That span stresses valves, cavitation margins, and control loops. Nozzle geometry matters. Canted jets reduce direct ground impingement and cross-coupling. And all of it must fit a propellant budget sized through pessimism. Late start contingencies, gusts, and go. Arounds that are not really go. Arounds but small sidesteps to a safer pocket. The Sky Crane looks theatrical because it solves a theatrical problem. You need the rover to be low and clean at touchdown, while the engines must be high and dirty. Tethers do the separation. The winch pays out with centimeter-per-second finesse. An umbilical carries power and data until the last heartbeat. If a tether cuts late, design the geometry so the rover cannot be toppled by a departing jetpack. If a motor hiccups, fail it safe rather than yanking the payload. The flyaway trajectory is pre-planned to a crash zone chosen for boredom. All of this intelligence needs to talk, which is why communications is treated like another critical system, not an afterthought. During entry, a minimalist tone can sometimes leak through the plasma to Earth, a heartbeat that says, "I'm still here," even while orbiters overhead listen for a richer UHF stream. After touchdown, the rover triages its words. A simple carrier or tone, then a thumbnail image to confirm that cameras are alive, then the flood of health. If the primary antenna's line of sight is blocked by a stuck panel or a bad attitude, have a backup path that does not care. Redundancy isn't waste. It's insurance you definitely cash. Zoom out and you see a pattern. Mars EDL is an ecosystem of trades. Thin air means more area and more rocket. More rocket means more dust and more mass. More mass means bigger area and stronger chutes. Bigger chutes mean more violent openings and trickier cutaways. You loop those trades until a specific vehicle, for a specific site and season, closes with margins. The margins aren't hand-waving. They're baked into every layer: parachute strength bands, ablator thickness, integrals, engine throttle ranges, sensor fusion logic that refuses to believe any single source. The result is not invulnerability. It's a design that turns likely surprises into manageable nuisances. People ask whether AI will take over this choreography. In a sense, it already has. Terrain. Relative navigation is a form of onboard vision and inference. As compute budgets grow and models get leaner and more verifiable, you'll see more predictors that learn gust patterns in real time, more classifiers that spot safe ground faster through dust, more adaptive controllers that squeeze performance out of thin air plumes without oscillation. But Mars will never accept a black box. Every decision maker must be testable, explainable, and bounded by physics so that a surprise becomes data, not disaster. The destination is not glamour, it's routine. The goal is to make 7 minutes so rehearsed that the control room's terror feels performative. When that day arrives, it won't be because Mars got easier. It will be because our machines learned to doubt, to fuse, to veto, and to commit on evidence. They will still fall out of space at Mach numbers that make your jaw clench. They will still ride a parachute that snaps open like a thunderclap. They will still light engines over a world that answers with dust. And then the wheels will meet stone, as if it were the only outcome that ever made sense. So what comes after sky cranes and supersonic parachutes? New means landing more mass, with less luck, on rougher ground, while making less mess. The planet hasn't changed: thin air, real gravity, hard ground, but our toolkit is growing. Picture wider heat shields that blossom in space, engines that light earlier and smarter, and a playbook that treats landing as a campaign that begins in orbit and ends when dust around fresh tracks has settled. Start with the least photogenic problem: what rocket plumes do to soil. Plume surface interaction is a quiet mission killer. Hot exhaust strikes loose regolith, digs pits, lofts gravel, and throws up tan curtains that blind cameras. On the moon, that spray can fly for kilometers because nothing slows it. Mars's thin air spreads plumes and slows particles, but it still sandblasts optics and ricochets stones into belly skins and wheels. Engineers counter with geometry, throttle, and ground knowledge. Cant nozzles so jets do not drill straight down, avoid long hovers in favor of steady descents, and pick sites where buried rocks and soft drifts are mapped in advance. Preparing the ground sounds futuristic, but step one already exists: orbital reconnaissance. The next step is robotic civil engineering. Send small bulldozers or sintering bots first. They can scrape boulders, grade pads, or fuse grains into a crust with microwaves or concentrated sunlight, turning powder into something that resists excavation. A prepared pad lets engines sit lower, cuts the dust geyser, and gives guidance a precise aim point. Parachutes have a scaling problem. As vehicles get heavier, fabric mass climbs, line loads spike, and opening shocks grow brutal. That is why the future leans toward two paths. One is bigger, softer entry systems, deployable or inflatable decelerators that bloom into dish-like shields in space. Lower ballistic coefficient means earlier, gentler braking higher up, where heating is kinder and decisions are less rushed. Earth demos have already proved that giant, flexible aeroshells can ride hypersonic flow. The other path is thrust sooner. Supersonic retropropulsion. Thrust can carve a controllable bubble in oncoming flow and ride it. Mars is thinner and trickier, but the principle carries. Light engines well before a parachute would normally be cut and let thrust do what air cannot. The challenges are engine stability in buffet-rich flow and guidance that avoids flying into your own exhaust. Solve those and mass scales gracefully, because thrust scales with weight. Scale rewrites choreography. A 1-ton rover can hang under a sky crane. A 20-ton cargo stack cannot. Large landers will likely fly no-shoot profiles, huge aeroshell for hypersonic and transonic, then deep throttling methane, oxygen engines for the rest. Deep throttle is the superpower. The same hardware must pull hard and then whisper during the last meter. Valves must move fast without ringing, pumps must avoid cavitation, and control loops must catch gusts without exciting oscillations. Dust is the tax on every plan. Future landers will pair radars that shrug at haze with lidars that build three-dimensional maps through it, plus cameras with wide dynamic range. Expect multispectral vision. Near, infrared bands see through some dust better than visible, giving terrain relative navigation contrast when noon glare flattens shadows. Estimators will adapt on the fly, down-weighting vision when contrast tanks and leaning on radar and inertial cues until the scene recovers. Drones change the script. A tiny helicopter already proved powered flight in Martian air. Minutes before entry, an aerial scout could sample winds aloft and relay a live profile, letting guidance bias range trigger bands and engine light logic using a measurement, not just a forecast. After touchdown, the flyer can inspect the descent stage crash site, map dust fallout, check antennas and arrays, and quickly survey safe spots for the next vehicle. Orbit-to-surface integration grows tighter, too. Instead of a single plunge, some profiles may use a skip to sample the day's atmosphere, then commit on the second pass with better knowledge and relay geometry. An orbiter can loiter to catch every heartbeat through blackout and beam thumbnails down within minutes. EDL Day becomes a choreography for a small fleet, not a solo act. Materials and mechanisms evolve under pressure. Heat shields move beyond classic ablators to hybrid stacks tailored to local hotspots. Parachutes, where still used, get stronger weaves and ring-reinforced patterns that spread opening shock. Lines and mortars gain wider deployment envelopes. Engine bells trade a touch of weight for erosion resistance, knowing they will eat grit. Guidance gets less brittle. Today's terrain relative navigation matches pictures. Tomorrow's will predict which landmarks survive haze and where shadows move with local time. Hazard logic will grow from avoid rocks to prefer soils that won't liquefy under plumes. And controllers will add envelope protection that refuses commands likely to amplify oscillations in dirty flow. Human landings add one more column. Fail. Operational behavior. Expect triple redundant sensors, cross-strapped avionics, and propellant reserves sized to sidestep to a secondary pocket if winds ruin the first. Expect touchdown systems that tolerate one weak leg long enough for software to unload that corner, and crew displays that tell the truth in plain language, because the worst interface at Mars is a euphemism. Underneath the novelty, old virtues still rule. Buy time high with more area. Buy truth low with better sensing. Buy calm at the ground with smarter rockets and safer sights. Mars will not apologize for thin air and dust. It will keep punishing brittle scripts and rewarding designs that doubt themselves in all the right places. When the next generation makes 7 minutes feel procedural instead of theatrical, it will be because we stacked our tools so each buys seconds for the next and then used those seconds well. Parachutes and heat shields sound like simple hardware, but on Mars they are precision instruments tuned to a mood swing. The shield is the first contract with physics, the canopy is the second. If either one blinks at the wrong millisecond, the mission trades geology for ballistics. Start with the shield. A blunt body builds a detached shock that holds the hottest gas away from the structure and feeds the ablator a controlled diet of heat. Ablation is chemistry in service of survival. Resins char, gases blow out, and layers peel away, carrying energy with them. Engineers tailor thickness and recipe by map, not by average hotspots near protuberances. Bolts and seams get extra armor. Cooler zones stay lean to save mass. Separation must work in vacuum, vibration, and cold. One stubborn fastener at Mars can end a mission. Guided entry turns the shield from umbrella into wing. By banking, the capsule creates a small lift vector and rides density layers like a surfer on a curling wave. The guidance law watches deceleration, Mach number, and sense dynamic pressure, and chooses when to dive or when to float, keeping heating within what the ablator can swallow. The goal is humble and ruthless. Reach parachute time with the right combination of speed, altitude, and range, so the next tool can bite without tearing itself apart. Now the parachute, the most violent fabric in the solar system. On Earth, you wait for subsonic air to avoid shredding the canopy. On Mars, you do the opposite. You fire at supersonic speed because waiting would meet rock. Designs like disc, gap, band, and ring, sail look odd for a reason. Vents and rings tame shock-driven oscillations and spread loads across fabric and lines in the first half-second, when opening shock is a fist. Some systems use reefing temporary constriction of the canopy mouth to bleed the initial punch before full inflation. Range-triggered deployment keeps the chute honest. Instead of trusting a single altitude callout, the computer fuses deceleration history, velocity, and estimated distance to target to choose the moment. Warm, dusty air can thin the atmosphere and tempt an early fire. Cold, dense air can push you lower than planned. The trigger rides what the vehicle feels, not what last week's model said. Even after a clean bloom, risk does not stop. Winds shear between layers, the stack can yaw and pendulum. Guidance trims bank and uses the canopy like a crude wing to slide cross-range toward a safer pocket. Cameras open when the heat shield drops and immediately feed terrain relative navigation. The algorithm hunts for bold landmarks, crater rims, and shadowed mesas, and matches them to an onboard atlas to estimate where the chute is actually dragging you. If the ellipse drifts onto a boulder field, the aim point slides sideways before cutaway. Cutaway is a cliff edge. Stay tied too long and the canopy can drag the stack sideways just as rockets ignite. Cut early and you are still too fast. The back shell separates, the parachute becomes yesterday, and engines replace fabric. Mars throws up a tan curtain of dust. Sensors must keep telling the truth through the storm. Radar shrugs at haze. LIDAR adds depth when contrast survives. Cameras bracket exposures, and the estimator fuses what still makes sense. Control laws chase margins. Fast enough to catch gusts, not so aggressive that plumes dig a pit and bounce stones into the belly. Why obsess over the physical details? Because scaling hurts. Parachute loads climb faster than mass. Fabric weight becomes punishment. And a canopy that behaved for a small lander can flutter or rip for a bigger one. Heat shields that loved a 1-ton rover can run out of margin when payloads double. That is why you hear so much about larger aeroshells that bloom in space and about supersonic retropropulsion. The first lowers ballistic coefficient so you start braking higher, where heating is kinder and decisions are less rushed. The second replaces some drag with throttle, letting thrust scale with mass. Case studies prove the pattern. A rover that reached an ancient delta did so because precision landing and hazard detection vetoed bad patches on the fly. A stationary lander at high latitude threaded a cold, dense atmosphere whose timing would have fooled altitude-only triggers. Range. Trigger logic saved the day. In each story, the planet did not get kinder. The playbook got smarter. Sensors bring personalities and pitfalls. Inertial units can clip under peak G and must be caught by logic that inflates uncertainty for a beat. Radars can lock onto sloped walls and report phantom ground. Filters compare claimed altitude with vertical speed and thrust history to veto impossible numbers. Vision loses contrast in haze. Algorithms favor geometry over texture, so craters still register. The estimator, a quiet accountant, waits and downweights sources as the scene changes and never trusts a single witness. Everything ends at the ground. Wheels or legs want a gentle slope, sparse rocks, and soil that will not fluidize under plumes. Hazard maps built from orbit inform the target. But the last veto is local. The downward camera, the LiDAR speckle, the radar chirp that says, too fast for this height. Touchdown logic treats landed as a consensus, not a hunch weight on wheels, plus inertial quiet, plus radar zero before cutters fire and the jetpack flees. Then comes the first breath, a tone, a thumbnail, a panorama, and a quiet control room finally exhaling. The deeper you look, the less magic you see, and the more choreography, heat, fabric, math, and doubt stacked in a sequence that buys time for the next step. That is how Mars turns from a rumor into a place where fresh tracks exist. Next, we will rewind the physics itself, Mach, dynamic pressure, ballistic coefficient, and lift to drag, and translate the jargon that rules EDL into pictures you can feel, so that thin air and supersonic become numbers your gut understands. Let's turn the EDL jargon into pictures you can feel. Mach number is simply your speed divided by the local speed of sound. On Mars, the air is mostly carbon dioxide and far colder than Earth, so sound moves slower. The same true speed gives a higher Mach, stronger shocks, and harsher heating. At hypersonic speeds about Mach 5 and above air, chemistry wakes up. Molecules split and ionize, forming a thin plasma that blocks radio. During those seconds, the spacecraft is alone. Dynamic pressure is the push of wind on your palm when you hold it out a car window. In math, it's 1/2 times density times velocity squared. In plain language, speed matters a lot and density matters too. Mars offers vicious speed, but stingy density. Early in entry, the push spikes because velocity is huge. Later, near the ground, density rises, and the push spikes again. Parachutes and heat shields are qualified to survive only a certain band of that push. Drag is how you buy time. Drag force grows with dynamic pressure, with the area you show the wind, and with a coefficient that rewards blunt shapes. Blunt is beautiful. A fat shock stands off from a blunt shield and holds the hottest gas away while producing lots of drag. Engineers compress this trade into one number: the ballistic coefficient, mass divided by drag coefficient times area. Low ballistic coefficient is life on Mars because low beta vehicles slow higher and cooler. Lift to drag the L over D. Pilots love matters even for a flying saucer. Offset the center of gravity and bank the aeroshell, and you get a sliver of lift. Not airplane lift, just enough to surf density layers. That tiny lift lets guidance steer cross-range, shape peak heating, and arrive at the parachute window with the right cocktail of speed and altitude. Those S-turns you've seen in animations are exactly that. Bank one way, then the other, to bleed energy without cooking the shield. Atmosphere shape enters through scale height, the altitude over which density drops by a factor of E. Mars's scale height is larger than Earth's, so density falls more gently with altitude, even though the whole column is thinner. Think of a long, flimsy blanket rather than a short, heavy quilt. Entry nibbles at drag high up, then leans harder as you descend. Every timing cue when to bank, when to pop the chute, depends on where you sit on that curve on that day. Heating is the quiet killer and follows a cruel rule of thumb. Heat flux rises roughly with density times the cube of speed. Speed is the monster. You cannot change gravity, but you can trade speed for heat early. That's why area matters so much. Slowing higher slashes, total heat, load, and ablative shields are sized not for a single peak, but for the integral, how much heat is soaked over time. Margins come from summing the worst credible day, not the average day. G-loads are the price your structure pays for braking hard. 10 or more G for a few seconds is normal for robotic craft. Crews will demand less. Guidance spreads the burden by modulating bank angle so you don't spike loads beyond what bodies and bolts can stand. High G isn't just about comfort. Sensors can clip, valves can lag, and brittle mechanisms can crack when the needle pegs. Managing G is managing survival odds for both hardware and science payloads. Flow regimes create different villains. Hypersonic entry is about shocks, chemistry, and radiative heating. Supersonic is about stability and fabric. Transonic, the messy middle around Mach 1, is about buffeting and control reversals. Mars EDL sprints through all three in minutes. Your design must be graceful in each. A shield that stays trimmed at hypersonic angles, a parachute that blooms in a forest of shocks, and engines that behave in the echo chamber near the ground. Reynolds number the ratio that whispers laminar or turbulent matters, because turbulent flow dumps more heat into the shield. Predicting transition is hard, so designers assume turbulence early and size materials accordingly. If later tests show the boundary layer stayed laminar longer, that extra becomes comfort, not waste. A conservative call here protects you from dust-roughened surfaces and geometry quirks that can trigger turbulence earlier than wind tunnel models suggest. Energy is the currency you really manage. The vehicle arrives with a bank account stuffed with kinetic energy, 1/2 mass times velocity squared, and some potential energy from altitude. Almost all of the kinetic must be dumped in 7 minutes. You can spend it 3 ways. Into the air as heat with a big blunt shield, into fabric through a supersonic parachute, and into exhaust with throttled rockets. Lean too hard on anyone and it breaks. The shield overheats, the chute tears, or engines run dry. Stability sounds boring until you lose it. The aeroshell needs a gentle restoring torque when gusts shove it. Otherwise, it tumbles and cooks unevenly. That's geometry and center of gravity placement. Parachutes must resist breathing, pulsing inflation and deflation in shock. Riddled flow, ring. Sail patterns and vents tame that. Descent stages need control laws that are fast but not twitchy, so they don't chase dust-induced radar glitches into crater-digging oscillations during the last seconds. Why the mantra ballistic coefficient is life? Because thin air gives you little drag per square meter. You either grow area or accept violent heating and late, rocket-heavy descents. That is why you see inflatable or deployable aeroshells in the pipeline. They slash beta by blooming to dish-like diameters in space and ride entry higher and colder. It's also why you hear more about supersonic retropropulsion, lighting engines earlier so mass scales with a throttle, not just with fabric strength. EDL is not one maneuver. It's a stack of clocks that all want to be right at once. Close the loop means sense, decide, act fast enough that reality hasn't moved on. The most unforgiving loops are the ones you cannot rehearse at full fidelity on Earth. Hypersonic chemistry in Martian air, a supersonic parachute blooming inside shock, riddled flow, rocket plumes biting dusty soil in 1/3 gravity. Bridging those gaps takes proxies, cross-checks, and margins, and then layering them, so each buys seconds for the next. Drag modulation is the quiet superpower of a lifting aeroshell. Offset the center of gravity, and a bank angle creates a sliver of lift. Guidance schedules bank reversals, S-turns, to bleed energy without overcooking the shield. If density runs thin, the vehicle digs deeper by holding bank and aiming lower. If heating spikes, it floats higher for a beat. An estimator watches the deceleration trace like a heartbeat, compares it to models, and chooses the next bank that stays inside heating and G limits while guiding toward the parachute window. This is choreography by math. Spend just enough energy high up so you arrive with the right speed, altitude, and range when fabric takes over. Range triggering carries that humility into the shoot phase. Instead of trusting a single altitude, the mortar fires inside a window conditioned on sensed deceleration and estimated distance to target. If winds and thermal tides shove the stack outside workable bounds, guidance biases cross-range to recover, or at worst accepts a slightly long landing and hands more of the job to rockets. It isn't luck, it's a sliding plan with fuel in the pocket. Vision is the other revolution. Terrain relative navigation gives a falling robot a memory and a sense of place. A downward camera grabs frames at multiple exposures, so bright haze and dark rocks share the same picture. Each image is reduced to robust landmarks, edges, corners, crater rims, chosen because they survive dust and glare. The onboard atlas comes from orbital photos. The flight computer matches landmarks to that atlas and solves position and heading in real time. When the match is strong and consistent, confidence climbs and guidance shrinks the landing ellipse. When contrast drops, the estimator downweights vision and leans on radar, LiDAR, and inertial cues until the scene improves. Below the camera, hazard detection builds a 3D grid from stereo or LiDAR. Slopes above a few degrees and boulders above a threshold are painted red. Flat, rock, poor cells go green. The vehicle carries a keep-out map of things that can flip a rover or puncture a belly pan. In the seconds before cutaway, guidance searches the grid for the largest reachable green patch, then commits. The sidestep that follows looks casual, a few hundred meters of drift, but it's a mission saver. Communications thread through all of this like a lifeline that mostly can't help you. During peak heating, plasma eats radio. A faint tone may leak through, but orbiters overhead are the real recorders. They catch UHF breadcrumbs and store them for replay. Direct-to-Earth links are minutes late. By the time a tone hits a dish, the vehicle is either breathing or a crater. That's why the first packet after touchdown is small and decisive. A heartbeat, a thumbnail, and core health numbers. Redundant paths, direct tones, plus UHF relays turn silence from terror into a brief formality. Strategy starts long before entry. Site selection is as much about air and light as geology. Deep basins offer more drag but bring gustier boundary layers and long slopes that can fool radar. Highlands steal drag and shove more work onto rockets, but may offer cleaner winds and less dust. Lighting matters. Morning cools the air but flattens shadows. Afternoon sharpens relief but pumps crosswinds. Teams pick a season and local time that make cameras honest, shoots survivable, engines happy, and orbiters well-placed to hear the story. Testing is a quilt of stand-ins. Hypersonic tunnels are short and imperfect, so heat shield models are checked by arc jets that blast materials with plasma until chemistry and recession match. Parachutes can't be opened on Mars, so sounding rockets yank full-scale canopies at Earth-high Mach numbers and carefully chosen dynamic pressures that bound the Martian case. Engines can't fire on Mars, so test stands feed them dust and throttle them through ugly duty cycles, while microphones and pressure probes hunt for oscillations. Software gets the worst abuse. Frozen gyros, blinded cameras, lying radars, saturation, time skew thousands of injected faults until every single lie is caught by redundancy and voting. Supersonic retropropulsion straddles today and tomorrow. Light engines early and thrust carves a pocket in the oncoming flow. Guidance rides that pocket like a surfer rides a tube. Keep the engine stable in buffet and keep guidance from chasing exhaust. And thrust becomes the decelerator that scales with mass. Parachutes shrink or vanish entirely for the heaviest stacks. Big cargo forces choreography changes. A sky crane lowers a 1-ton rover with grace. A habitat or ascent vehicle can weigh 10 times more. The likely profile is no shoot. A huge deployable aeroshell for hypersonic and transonic. Then deep throttling methane, oxygen engines take you the rest of the way. Methane and oxygen are logistics, not romance. You can make them from Martian air and ice, and they store better than hydrogen for months of cruise. Deep throttle is the superpower. Pull hard high up, then whisper at 1 or 2 meters without digging a crater. That stresses valves, pumps, control loops, and nozzle geometry. Canted bells and fast. Well, damped controllers keep plumes from excavating the site or bouncing stones into the payload. Dust is the forever adversary. Plumes pick it up, winds keep it up, optics hate it, radiators clog with it. Future landers will pair radars that shrug at haze with lidars that build depth maps through it and cameras that see a bit into the near infrared, where some dust is kinder. Expect sensor fusion that weights sources dynamically. Vision when contrast is good, radar when it's bad, lidar when the ground is close. Expect old-fashioned geometry, 2 canted engines, short hovers, and prepared pads to cut the geyser. Small flyers add a new sense organ. A scout helicopter can sample winds along the descent corridor hours before entry, giving range trigger logic measurements instead of forecasts. After landing, the flyer can image the descent stage crash zone, check dust on arrays, and map safe approaches to outcrops the rover wants, but the lander couldn't risk. For human missions, the word abort returns to Mars EDL. Cargo can accept single-string boldness, crews cannot. Architectures will pre-position return propellant, use triple redundant sensors and cross-strapped avionics, and carry divert fuel to slide to a secondary patch if a last-second gust trashes the primary pocket. Touchdown systems will tolerate 1 weak leg long enough for software to unload that corner, and crew displays will tell the truth in plain language. G-loads will be lower, engine throttles deeper, and communications more layered so that silence is rare and short. Above all, nothing mystical hides inside the 7 minutes. It is energy accounting under bad conditions, stingy air, real gravity, imperfect forecasts, and sensors with personalities. The craft that wins is the one that doubts smartly fusing, vetoing, and committing only when multiple truths line up. Do that, and Mars stops feeling like a gamble and starts feeling like a procedure you can repeat. Behind every 7 minutes is a room that doesn't land a spacecraft, it listens to one. When the entry clock starts, mission control becomes a theater of silence. Heads are down, eyes track a timeline with colored bars. Cruise separation, entry interface, peak heating, parachute deploy, heat shield drop, backshell separation, powered descent, sky crane, touchdown, fly away. Each bar is a promise made months earlier by analysis, and test what should happen, roughly when, and how it will look. The choreography on Earth begins long before the vehicle sees Mars. Teams run sims, scripted nightmares. A red team injects faults, a gyro freezes, a radar ghosts, a camera blinds in dust. An ops console must triage, decide, and speak in seconds. Every console has guarded words. Nominal means as expected. Off, nominal, means within margins, but watch it. Tango Delta nominal, touchdown confirmed, isn't a single shout. It's the sum of hundreds of small greens. The Deep Space Network is the stethoscope. Giant dishes at Goldstone, Madrid, and Canberra trade off as Earth turns. Some links are just tones narrowband beeps that say, "This event fired," even at low signal, to noise. Others are UHF relays through orbiters overhead, buffered and played back minutes later. Direct-to-Earth bits are precious and sparse. The fat science tapes will wait for rover days. During EDL, the rule is minimal words, maximum meaning. Go, no-go moments are quieter than movies suggest. Weeks before arrival, leadership commits to a season and local time, chosen to balance density, lighting for cameras, relay geometry, and dust risk. On the day, only small choices remain. Tweak the entry aim point by a few kilometers, rotate the corridor by tenths of a degree, arm or disarm a backup trigger. You don't wave off Mars, you shave edges off risk. What does the room actually see? Timestamps crossing expected windows, a deceleration peak rolling off, a flag that the mortar fired, another that the heat shield separated, a Doppler shift that hints engines are throttling. Vision navigation doesn't stream pictures. It spits confidence numbers how strongly landmarks match the onboard atlas. Hazard detection votes safe pocket and sends a vector. None of this is heroic alone. Together it is a story you can trust. Rehearsal chases away ego. Ops binders hold pages you hope never to turn. Loss of radar, loss of LiDAR. Loss of vision, stuck pyro. Late cutaway. Early engine light. For each, if A and B agree, do C. If not, hold and seek D. The vehicle is alone out there. The checklists are for the humans. So when a tone is late or missing, eyes drift to the right line. Not to panic. If touchdown happens, a second ritual begins. The first, light plan. The vehicle triages its own health, then speaks in a set order. A heartbeat, tone, first. A tiny engineering image next, something easy to compress, like a thumbnail from a navcam, proof that optics, storage, and downlink work. Then core health. Temperatures, pressures, battery, bit flips. Only after that does the rover stretch, raise a mast, turn a head, or sniff the wind. The first panorama the public sees is actually test 3 or 4. Surface risk doesn't clock out at touchdown. Last meter plumes can fluidize soil. A legged lander may settle and tilt. Rovers mind wheel sinkage and avoid sugar dunes that swallow tread. Winds can still shove. Controllers plan a Sol 0 that is mostly listening. Check dust on arrays, measure sky brightness, ping the descent, stage rec to map debris, confirm the antenna has a clean view. Even the sun's position matters. A low sun can blind cameras with glare, just when hazard avoidance wants contrast. Every success the public sees as a moment is, internally, a ledger Margins spent versus margins saved. Did parachute timing drift late because density ran thin? Did the descent stage throttle deeper than expected to fight a gust? Did hazard logic veto the primary pocket and slide to plan B? Answers feed back within hours. Teams patch Monte Carlo models with what Mars actually did and tell the next designers which corners were too tight. Culture keeps you honest. The best Mars teams assume they are wrong and work to prove they're right. Independent navigation reconstructions are run by separate analysts using different tools. Reviews are chaired by people who did not design the system under review. Promortems ask, if we were going to lose this mission tomorrow, how would it happen? Then someone makes that happen in simulation until a countermeasure is real, not promised. There is human theater, too. The public watches to be present for a first breath on another world. Engineers watch to be accountable to their own work. The quiet, the late radio, the hard math, these are features of exploring at the edge. When the room finally hears a healthy tone and a tiny, dusty thumbnail arrives, the cheer is not relief alone. It is gratitude that a plan survived contact with a planet. Now look toward the first crewed Mars landing. The room will look similar, but margins will be fatter and the language plainer. Nominal won't be good enough. Comfortable will. You'll hear about diverts, a powered sidestep to a secondary patch if winds poison the primary. Engines will throttle deeper and faster. Touchdown systems will be fail operational. A leg can misbehave and software will unload that corner. Communications will be layered so the crew never wonders whether Earth is listening. What doesn't change is the core bargain. You manage energy with area, fabric, and fuel. You manage truth with sensors that disagree constructively. You manage timing with algorithms that believe evidence, not wishful models. You manage dust with geometry and restraint. Do all four, and Mars turns from a gamble into craft. Next, the hardware through stories. Viking's rocket legs, Pathfinder's airbags, MER's bounces, Phoenix's polar touchdown, and the sky crane that lowered car-sized rovers into ancient lake beds. Each wrote a line of the EDL playbook we fly today. Begin with Viking. In 1976, 2 NASA landers arrived behind blunt aeroshells that took the heat, used a supersonic parachute to grab what little drag Mars provides, then throttled rockets on legs to finish the fall. Viking proved the end-to-end recipe guided entry. Shoot, powered descent could be flown on another world. Radar watched the ground, engines throttled cleanly, and a tripod platform settled without drama. More than a milestone, it became a template. Later missions would bend, not break, for decades. Pathfinder in 1997 flipped the script with audacity and thrift. Instead of riding rockets to legs, engineers wrapped the lander in giant airbags. After guided entry and a supersonic chute, solid rockets in the backshell slowed the stack. The airbags inflated high, and a bridle cut the lander loose. It dropped, bounced, and rolled more than 15 times before coming to rest. Pedals opened, and tiny Sojourner drove down a ramp. The lesson: for small payloads, you can trade precision for forgiveness and let Mars absorb your errors. Airbags turn chaos into cushion, converting violent unknowns into survivable bounces that keep the core hardware safe. Airbags scaled once more for the Mars exploration rovers, Spirit and Opportunity, in 2004. The choreography echoed Pathfinder heat shield, supersonic chute, backshell retro rockets, inflate, cut, bounce tuned for bigger payloads and rougher sights. Documentation even notes the rockets on the backshell fired until the lander was roughly 8.5 meters above the ground before release, highlighting how thin air forces rockets to share the job with fabric. MER's success wrote another rule: for a few hundred kilograms, airbags are elegant. Beyond that, fabric mass, seam loads, and opening shocks turn cruel. Powered descent returned with Phoenix in 2008. Headed for high northern latitudes and buried ice, Phoenix rode an aeroshell and supersonic parachute, then cut away and lit throttleable engines for the last stretch. It became the first successful propulsive touchdown on Mars since Viking, and its plan deliberately separated the fall into clean phases: entry, shoot. Rockets backed by software that treated landed as a consensus of sensors rather than a single switch. Phoenix was a technical and cultural correction after 1,999's heartbreaks. Distrust brittle triggers, qualify parachutes across a band of dynamic pressures, and give engines the throttle authority to whisper in the final meters instead of hammering holes in the soil. Insight, a decade later, reused Phoenix's architecture almost page for page by design. If you want seismology on a calm plane, don't reinvent the fall. Refly what worked and spend risk on science. Insight's EDL showed the value of heritage. When a design is mature, the most valuable landing is a boring one. Then came the sky crane. Curiosity in 2012 was too heavy for airbags and too precious for a tall deck and ramps. The answer was theatrical and logical. A rocket-powered descent stage lowered the rover on 3 tethers, and an umbilical, cut when weight on wheels was sensed, then flew away to crash elsewhere. Keep engines high so dust and gravel don't sandblast optics. Keep the center of mass low so first contact is stable. Put wheels on soil, not on a platform. An orbiter even caught the parachute and rover mid-descent, a real photograph of an idea many called crazy until it worked. Perseverance in 2021 flew the same sky crane with crucial upgrades. A stronger supersonic parachute, tortured on Earth so it wouldn't fail on Mars, held its shape in shock-riddled flow. More importantly, terrain relative navigation gave the falling stack a sense of place. A downward camera matched live images to an onboard atlas and let guidance slide into a safe pocket amid Jezero's boulders and scarps, turning land between the hazards from slogan to requirement. Precision wasn't a flourish. The science lived in the dangerous bits, and machine vision made those bits landable. Line these landings up on a wall and a pattern emerges. Viking taught powered descent and conservative triggers. Pathfinder and Mir made airbags a workhorse for small payloads, buying safety with bounce. Phoenix and then Insight restored rockets to the repertoire and hardened logic against sensor illusions. Curiosity invented the sky crane to deliver a car upright with no ramp. Perseverance added machine vision so a robot could veto bad ground in real time. None of those choices were stylistic. Each answered a physics problem with the least brittle trade on offer. The rulebook they wrote is blunt. Mars's air is under 1% of Earth's, so parachutes alone can't tame a heavy fall. You either add area, add thrust, or both. Airbags are brilliant until fabric mass and opening shock outrun your payload. Powered descent is flexible, but plumes can blind you and fling stones. Keep engines high or prepare the ground. Cameras can see through the lie of models when dust steals contrast, but only if you give them dynamic range and an atlas to match. And whatever declares landed must be a chorus, not a solo. Leg switches, radar, accelerometers, and guidance all agreeing before cutters fire and a jetpack flees. These aren't museum pieces. The Mir range trigger logic echoes in today's parachute deployments. Phoenix's radar filters and propulsive choreography show up in Insight. Curiosity's sky crane is now standard for heavy rovers. Perseverance's terrain relative navigation is baseline for any mission aiming at scientifically rich, hazardous terrain. The playbook is cumulative. Once a trick buys seconds, it stays, and those seconds get spent on something braver. Whether that's rougher ground, heavier payload, or tighter ellipses, watch the highlight reels and you see hero shots. A rover dangling on cables, a tan plume, a tiny horizon. Inside those frames sit decades of trades, area for heat, fabric for mass, throttle for control, vision for truth. Viking to Perseverance isn't a string of miracles. It's a series of negotiated settlements with thin air and hard ground. Every line in today's EDL script has a mission's name next to it, and every future line will too. Next, we'll stack these lessons into a forward plan. How wider aeroshells, earlier engines, smarter vision, and prepared ground can make 7 minutes feel like procedure for cargo and, eventually, for cruise. Turn the rulebook into a plan. If the goal is routine cargo and later, cruise, the recipe is not one trick, but a campaign choices made months before arrival that buy seconds during the 7 minutes that matter. Begin with the calendar and the map. Pick a season and local time that make cameras honest and fabric survivable. Lighting with strong shadows for vision. Density in the middle of the expected band. Winds without sharp shear. Choose sites with science in reach but landing pockets that are flat, rock-poor, and mapped from orbit down to boulder scale. Deep basins offer more drag but gustier boundary layers. Highlands offer calmer air but steel drag and tax rockets. Decide which tax you can afford and size margins around it. Precursor robots go first. Small scouts grade a pad or fuse soil into a crust so engines won't dig and spray stones. They drop a few shoebox beacons around the ellipse little radio lighthouses that help the incoming vehicle validate terrain, relative navigation, when dust flattens contrast. A flyer samples winds aloft the day of landing. Its profile nudges range, trigger bands, and where engines first light. Arrival treats entry day as 2 acts. Act 1 is a skip. Graze the upper air, read density and winds for real. Then loop for Act 2 with updated guidance and relay geometry. You cannot wave off Mars entirely, but you can trade minutes to cache in certainty. The Deep Space Network and an orbiter overhead are primed for tones and UHF, so the control room hears breadcrumbs even while plasma eats most radio. The aeroshell blooms big. A deployable or inflatable heat shield slashes ballistic coefficient, so braking starts higher and colder, where heating integrals are gentler and timing is less frantic. The blunt body is trimmed to be slightly lifting. Bank reversals bleed energy without cooking the shield and steer cross-range toward the safe pocket you scouted months ago. Guidance watches the deceleration trace like a cardiogram and rides density in real time rather than a cartoon atmosphere. Parachutes become optional. For moderate masses, a stronger ring sail or disc gap band canopy, qualified across a wide dynamic pressure band, still buys altitude, then gets cut decisively before it can drag you sideways. For heavy cargo, thrust takes that job. Supersonic retropropulsion lights early, carving a controllable pocket in the oncoming flow. Controllers are tuned not to chase buffet into oscillations. Nozzles are canted to reduce direct ground drilling. Throttle response is deep and quick, so engines can pull hard high up and whisper in the last meter without geysering dust. Vision and skepticism run the terminal minute. A downward camera grabs bracketed exposures. Near-infrared bands keep edges when visible light goes milky. LiDAR paints a depth grid. Radar keeps the metronome straight through haze. The estimator fuses them, downweighting any source that disagrees with physics. Terrain relative navigation locks onto bold landmarks and shrinks the ellipse. Hazard detection vetoes, micro-traps, boulder clusters, steep aprons, soil patches that fluidize under plumes. If the primary pocket turns red in the last seconds, divert logic slides to a secondary patch without drama. Landed is a consensus weight, on wheels plus inertial quiet plus radar agreement before cutters fire or throttles close. The ground matters as much as the fall. Prepared pads turn a dust geyser into a dust puff and keep gravel from ricocheting into optics and radiators. If you cannot prepare, geometry helps. Keep engines high, minimize hover, touch, and commit. After contact, do not rush. A heartbeat first, a thumbnail second, core health third. Only then stand, raise a mast, or unfold arrays. Early images include the descent stage crash site. Debris maps become rules for where the rover should not drive. For crews, fail operational replaces fail safe. Sensors are triple and cross-strapped. Computers vote and can isolate a liar. Propellant margins carry a guaranteed sidestep to a secondary pocket. Touchdown systems tolerate one weak leg long enough for software to unload that corner. Cockpit displays use plain language and physics units that match what pilots train on: pounds versus newtons, footnotes. G-loads are kept below human comfort limits, not by luck, but by bank scheduling and bigger area high up. Testing becomes a ladder you climb years ahead. Heat shields are punished in arc jets until chemistry, recession, and temperature histories match models, tile by tile. Parachutes, where used, are yanked at Earth-high Mach numbers and the right dynamic pressures on sounding rockets. Seams and rings are redesigned until nothing tears in the first half-second. Engines run dusty duty cycles on stands and in free flight tests that bounce thrust across the envelope. Plume-soil interaction is measured in vacuum chambers with Mars-like regolith, so nozzle angles and throttle ramps are chosen by data, not taste. Software swallows thousands of faults, frozen gyros, blinded cameras, clipped IMUs, skewed clocks, until every single lie is caught by redundancy and voting. Networks close the loop. Orbiters fly as navigators and recorders, not just radios. They relay EDL telemetry, provide fresh wind and dust maps in the days before arrival, and serve as an optical constellation that helps terrain, relative navigation confirm position when the surface is hazy. Surface beacons left by precursors become local pseudolights, tiny GPS stand-ins that cut estimator uncertainty in the last kilometer. Logistics tie the plan together. Methane-oxygen engines are not fashion, they are supply chain. You can make both on Mars from air and ice. So the same hardware that lands cargo becomes the hardware that lifts samples or crews later. Deep throttle-wide ratios without ringing valves is the superpower that lands heavy gently. Dust-resistant radiators, filters, and covers acknowledge that the first hour after touchdown is the grittiest hour the vehicle will ever live. What fails in this plan? Models that drift from reality and single-point truths. The countermeasures are baked in. Range triggers that listen to what the air is doing today, not last week. Estimators that inflate uncertainty when any sensor saturates. Parachutes that are optional rather than mandatory. Engines that light early enough to forgive a thin day. Culture finishes the job. Independent reviews, separate navigation reconstructions, promortems that force you to kill your own mission on paper before Mars can try. If this sounds like overkill, that's the point. Routine is just paranoia that paid off. You buy time high with area. You buy truth low with sensing that disagrees constructively. You buy calm at the ground with smarter rockets and, when you can, a prepared patch of soil. Do those three on purpose, and the deadliest 7 minutes become a procedure you execute, not a cliff you pray over. In the next chapter, we'll zoom in on sample return, how a lander, a fetch rover, and a miniature rocket thread the same thin air twice down to deliver and up to escape, and what that choreography borrows from everything you've heard so far. Sample return is Mars EDL with a mirror. You thread the thin air once to land a lab, then again in reverse to launch a miniature rocket. The choreography links machines that each have a hard job and, together, attempt something no one has done: bring pieces of another planet to Earth, sealed for science and safe for life here. Start with the down leg. A sample retrieval lander arrives behind a wide aeroshell, often deployable to lower its ballistic coefficient, so braking starts higher and cooler. It flies S-turns to manage heating, then either pops a supersonic parachute or, if mass demands it, lights engines earlier and skips fabric. Powered descent keeps nozzles canted and hover time short, so plumes don't excavate gravel toward cameras, arrays, or Perseverance's cache. Terrain relative navigation and hazard detection pick a flat, rock-poor pocket within driving range, and the lander settles without painting the target zone with dust. Cleanliness is a second gravity. Planetary protection rules demand that what goes down stays clean and what comes up stays sealed. The lander's sampling system acts like a surgical team. Dust covers peel, tools present, and tubes pass through glove box, like enclosures where air is filtered and chemistry is controlled. Every latch and seal is witnessed by sensors. A wrong torque or a missing click is a no-go that triggers a retry. The container that will fly to orbit the orbiting sample canister must survive vacuum, thermal swings, and a rocket launch while staying hermetic. Think pressure vessel the size of a thermos, but built like a spacecraft. How do tubes reach the arm? Redundancy. Plan A is the rover that cached them. Perseverance, driving to the lander and handing off through a port. Plan B is aerial. Compact helicopters with gripping feet, evolved from the demonstrator that proved flight works in Martian air. Retrieval flyers add a claw and a belly bay. They hop to a tube, perch, grab, and shuttle it back like bees feeding a hive. Flyers by reach across ripples and boulder fields. The lander cannot risk and keep wheels off fragile soils that would swallow a rover. Now the upleg. The Mars Ascent Vehicle, a two-stage pencil bolted to the deck, tiny by launch pad standards. It is historic, the first rocket to lift off from another planet. Ignition adds a plume, surface hazard, so protective shields and canted nozzles keep the opening seconds from sandblasting nearby hardware. Guidance is simple on purpose. A pre-programmed pitch profile aided by a radio beacon from the deck, so the little rocket doesn't need delicate star trackers in a dusty sky. The sealed canister sits up top. After burnout, the second stage spins it for stability and releases it into a clean, trackable orbit. The target is not space, it's a moving net, an orbiter waiting in a specific lane. Rendezvous is robotic ballet. The Earth-bound orbiter uses optical and LiDAR navigation to approach the gently tumbling canister, swallows it with a capture cone, and tucks it into a double-walled vault. Inside, a small handler verifies seal pressure, wipes exterior dust, and shelves the treasure for the crew's home. Count the hidden EDLs. 1. Land the retrieval hardware on Mars. 2. Land into Mars orbit with a rocket that must hit a time and place window measured in minutes and kilometers. 3. Years later, land the samples on Earth inside a blunt capsule that must survive our own 7 minutes fiery entry, drogue and main parachutes, and a hard Earth touchdown with containment intact even on a bad day. Cleanliness is not cosmetics. If Earth microbes ride to Mars in a crack, future life detection results become suspect. If Martian organics ride back out of a leaky seal, a sterile Earth lab breeds noise. So hardware that touches samples is baked, purged with sterile gas, and kept behind covers until minutes before use. Purge lines sweep interfaces so dust cannot creep in. Greases that outgas are banned near the vault. Every time a door opens, sensors log particles and pressure. If counts wander, operations pause, and the system repurges or swaps to a backup path. Timing arcs across the campaign. Weather picks a landing season with honest shadows for vision and manageable winds for parachutes. Flyers prefer dawn calm. The lander prefers afternoon lighting that makes hazard maps pop. Orbital mechanics sets launch windows for the ascent vehicle. If a regional dust storm surges, the plan stretches by days, not hours, with batteries and cryogenic margins sized accordingly. Navigation is rehearsed with hardware in the loop. Cameras stare at printed Mars terrains. LiDARs scan dusty chambers, and guidance is pounded with wind and density surprises until it learns to distrust easy answers. Control rooms rehearse custody as much as descent. A chain of identity follows every tube from cache on the ground to socket in orbit. Telemetry includes barcodes, seal pressures, temperatures, torques, and close-up images, so an engineer on Earth can prove that the right lid really sealed the right sample. If a hinge stutters, the playbook includes swap-outs and parallel ports. If a flyer drops a tube, cameras mark the spot, and a second approach is staged from a safer angle. The paperwork is dull on purpose. Here, documentation equals science. Now the return, the last 7 minutes. Months after rendezvous, the Earth entry system detaches from the orbiter and aims for a desert range. The capsule is a Viking cousin. Blunt body, char, happy heat shield, drogue, and main parachutes sized for dense air. Inside sits a vault within a vault. Even an off-nominal landing must not breach containment. Foam, crushable structures, and break-before-leak joints ensure bad days fail safe. Recovery teams in clean suits treat the site like a forensic scene. Tents, filtered air, rapid transport to a new-build lab that exists to open the vault slowly, cleanly, and with worldwide eyes watching. Why risk so much choreography? Because a few hundred grams of documented rock and dust can answer what rovers cannot. You date layers to decades instead of centuries. You read organics down to molecules. You weigh isotopes that reveal the temperature and chemistry of ancient water. You test habitability with confidence bounds fit for textbooks, not tweets. Every seal and sensor is a bet that those answers will be trusted for generations. Everything we have learned about EDL shows up here with extra skepticism. Big shields by time high, range triggers and vision by truth low, rockets whisper near the ground. Dust is treated like an adversary with a lawyer. Add custody, redundancy, and patience, and you get a mission that lands, launches, and lands again, one thread through thin air, then another, so that someday a scientist on Earth can read Mars with a microscope instead of a camera. In the end, Mars doesn't hate us, it's just honest. Thin air, real gravity, hard ground. It tells you exactly what it takes to arrive. Area to buy time, sensing to buy truth, rockets to buy calm, and a culture that refuses to believe any single instrument or prediction. When people ask, why do Mars landings keep failing? The plain answer is that failure is baked into the environment and designed out of the plan, one lesson, one margin, one scar at a time. Now picture the last 60 seconds from the rover's point of view. A tan curtain boils beneath you. Radar ticks. LiDAR draws a ladder of distances. The downward camera catches a knife-edge shadow that matches a crater rim in its atlas and nudges the aim point 10 meters left. Engines whisper, then breathe harder, then whisper again. The winch pays out cable, smoother than a violin bow. Wheels touch, weight on wheels. Accelerometers settle. The umbilical severs like a sentence ending with a period. Above, the jetpack rips away to die somewhere safe. The rover is alone, standing and hearing Mars. That choreography is the seed of everything that comes next. Sample return, cargo stacks, habitats, ascent vehicles. The pieces will evolve, the physics won't. Wide shields still buy time high. Vision still chooses ground. Rockets still make the last meter boring. The increments matter. A stronger weave in a supersonic parachute isn't just fabric. It's seconds when seconds are life. A deeper throttling valve isn't just hardware, it's a smaller crater and a cleaner lens. A better estimator isn't just math, it's a veto of a lie before it becomes a crater. Imagine the first human landing. The vehicle will look more like a compact building than a rover tens of tons, methane oxygen engines, a low belly on a wide base. The playbook shifts. Likely no parachute, a huge deployable aeroshell for the fireball, engines earlier, engines smarter, engines canted to spare the ground. A prepared pad would be gold. If we can't pave, we at least aim for soil we've mapped grain by grain and minimize hover. The cockpit language stays plain: altitude, vertical speed, fuel, a big divert arrow. Fail, operational rules. One sensor can lie and the landing still completes. One leg can complain and software unloads that corner. One gust can shove and the throttle has room to answer. Then someone climbs down the ladder and stands in the same unhurried air we've modeled for decades. Dust hangs a little too long. The horizon feels very close. The sky is butterscotch. A breeze pushes sound sideways. Cameras trained for rocks watch a person take a step on ground we once knew only as pixels. That moment will have been purchased by EDL, the most unromantic part of exploration becoming its most enabling. Why tell this story now? Because Mars exploration sits at a hinge. We can keep landing rovers that take heroic selfies with delta rocks, or we can turn those 7 minutes into a solved problem and aim heavier, rougher, closer to the places that answer old questions well enough to write new ones. When 7 minutes becomes procedure, scientists get to be picky. Land on the contact between two layers 15 meters apart. Thread between twin boulder fields to reach an outcrop flagged from orbit. Pick the southern edge of a fan because that's where the oldest clays hide. Precision is not a flourish. It is permission to ask better questions. The near-future tools are already on the bench. Inflatable or deployable aeroshells packed tight and bloom huge, slashing ballistic coefficient so braking starts higher, cooler, and calmer. Supersonic retropropulsion, guided by controllers that don't chase buffet into oscillations, lets thrust replace drag when fabric won't scale. Cameras that see a bit into the near-infrared keep edges through noon haze. LiDARs paint depth when contrast dies. Radars shape their beams to ignore tilted walls and false ground. Estimators reweight sensors on the fly and inflate uncertainty the instant anything saturates. Terrain relative navigation stops being a stunt and becomes a habit match. Veto, sidestep, commit. We will still lose vehicles. A hinge will stick. A sensor will clip. A dust wall will pop up faster than a forecast. But if the architecture is layered with systems that doubt one another constructively, a single bad day won't become a crater. You'll hear more off-nominal calls that end in boring touchdowns, more Tango Delta nominal moments that ride on 5 quiet saves you only read about in post-flight notes. That is what learning by doing really means at Mars. Not swagger, but better odds. There's a quieter payoff. The guidance that keeps a parachute honest can steer aircraft-thin drones through afternoon shear. Plume soil data that keeps stones off a rover's belly will tell construction bots how to center runways and raise berms. Methalox engines that land cargo will later light for ascent with propellant made from air and ice. EDL isn't a single technology. It's an ecosystem that bootstraps presence. Master it. And you don't just land, you arrive with a plan for the next step. When we started this journey 2 hours ago, we opened with a cliffhanger. An icon on a screen, an entry interface, a room that could only listen. Now you know what lives inside those 7 minutes, the physics, the tricks, the traps, the fixes, and the future. You've heard why parachutes are both savior and saboteur, why heat shields are chemistry with a stopwatch, why engines must learn to whisper, and why cameras have to be skeptical. You've seen why Mars punishes brittle scripts and rewards designs that doubt, fuse, veto, and commit on evidence. So, the next time you hear 7 minutes of terror, translate it. It means millions of lines of code that refuse to believe a single sensor. It means fabric tortured until it blooms perfectly once. It means a shield that peels like an onion with just the right tears. It means engines that can change their mind in milliseconds. It means a team that practiced being wrong until it learned how to be right. And it means this: somewhere, not very long from now, a vehicle will hit a Martian morning, ride a huge, soft shield, light engines sooner than you expect, see through its own dust, and set down on a patch of ground a human geologist actually asked for. The room will wait. A tone will arrive late, as always. A thumbnail will show tan grit and the foot of a ladder. The cheer will burst like a parachute opening. For a planet that never promised to be kind, that will be the kindest sentence it can offer. We made it. Tango, Delta, Nominal.